Step 16, I can solve polynomial equations by graphing and factoring. So first let's talk and clear up a little bit of vocabulary confusion. A lot of times, and I'm guilty of this myself, we use some of these terms extremely interchangeably, but these terms do have very specific definitions, and I want to make sure it makes sense how they're related. So sometimes you hear us refer to roots or zeros or solutions or factors, and we kind of gloss over it and say, yeah, you know, they're all the same thing. But let's take a closer look. So C is a zero of a polynomial function. What does that mean? Well, if I look at this polynomial function here, x cubed minus 4x, C would be any number like -2, 0, or 2. -2, 0, or 2. And let's use this as an example. Put an example next to it. So if my polynomial function is f of x equals x cubed minus 4x, then the zeros would be -2, 0, and 2. C is a root or a solution of a polynomial equation. And what that means is if I put 0, for instance, into the equation, I get a true statement, meaning 0 is a solution. That's what it means to be a solution. You can be a solution to an equation. You can't really be a solution to a function. Also, if I wanted to write factors of this polynomial, I could write x plus 2. I could put x plus 0. And I could have x minus 2. Those would be the factors where you replace C with, or you replace this letter C with all the different numbers to make the factors. Finally, if C is real, then C comma 0 is an intercept of the graph. So looking at this picture, this is an x-intercept, this is an x-intercept, and this is an x-intercept. And again, we tend to get a little bit lazy about being very precise with those terms, but I just wanted to start off by kind of clearing that up just a little bit. Okay, so we can solve functions by graphing. All we need to do, if we want to solve an equation, it's going to be C. So if we look at the graph, it's going to be the x-intercepts. Or if we look at the function, it's going to be one of the zeros. So if we need to solve this equation, one option is to do it by graphing, to graph a picture of it and look and see, well, where does it cross the x-axis? And it crosses here and here. So my solutions to this equation would be x equals -5 or 2. Pretty nice, huh? Here we have a linear function. Now, I'll be honest, this would not be extremely difficult to solve. We would subtract 2 from both sides, and then we would multiply by 3, and we have our answer. Not very difficult to solve. In fact, solving it by graphing would probably be more involved, but let's try it. Okay, let's begin at 2, and we're going to go up 1, right 3, up 1, right 3. And then when we connect this with a line, as neatly as we possibly can, we can look and see where this line crosses the x-axis. And that's going to be our solution. So as we look closely, we see that it crosses at -6, which is exactly what we got when we solved algebraically. So I just wanted you to see the similarity between solving an equation and graphing a function and how you get the same answer. Here's an example of a real-world problem. Adrian downloaded albums to his smartphone. Each album costs $1.25, so it's $1.25 times each album, and he had to pay this fee of $8. If the total cost for the download and the subscription was $15.50, how many albums did he download? Let's solve by graphing the related function. So to graph the related function, this is an equation. Let me get it into function form by subtracting 1550 from both sides. Subtracting 1550 from both sides gives us 1.25x minus 750 equal to 0. Now all I have to do is replace this 0 with a y. Because remember, to graph a linear function, we need to have an x and a y value. So I'm going to begin at -7.5 on my graph, and I'm going to go 1.25, which is the same thing in a fraction as 5/4. But I like 5/4 better because now I can see it as a slope. So up 3, 4, 5 over 4. And connecting these with a line, as neatly as possible, we can see now that it crosses at 6. So x equals 6. Now again, you might be saying, well, wouldn't this be easier to just solve algebraically? And it might be. But then we get to problems like this. These are much more complicated to solve algebraically, which we are going to learn in this series of Step 16 videos. But solving this one graphically is appreciably easier. So I'm going to go into Desmos, split my screen, and we're going to type this in, plus 5x squared plus 2x minus 8. And you can easily see that when I graph the related function, this is what I'm graphing. And when you type that on Desmos, you don't have to put equals y, but you certainly don't want to have equals 0 or it would not work. Let me show you what happens if you do that. See, you just get these straight lines up and down. We actually want to see the curve. And you can see that it crosses at -4, -2, and 1. So x equals -4, -2, or 1. That is our solution. What happens though if we don't have graph paper or graphing technology readily accessible at our fingertips? Well, when that happens, we really need to change gears and try to factor to solve or solve algebraically. Some of these problems are very difficult to factor, like this first one. How would we factor this? It's been a while. So let's take a step back and review factoring first, because it's been a while since we've done very much factoring, and we're going to review some factoring as well as learn a few new tips and tricks and techniques to help us solve by factoring. So regardless, this is one thing that everybody wants to forget. For any number of terms, always first check for a greatest common factor. If you have a difference of, or if you have two terms rather, you could be checking for a difference of squares, a sum of cubes, or a difference of cubes. And these are just formulas that we can apply when we have situations like that. If you have three terms, you can check for, is it a perfect square trinomial? Kind of like we studied back when we did completing the square. Or you could factor using our method where we take the coefficient of A times the coefficient of C and multiply them together and look for factors. If you have four or more terms, we can factor sometimes by grouping. So let's practice this with a variety of different problems. So again, we're going to try to find the greatest common factor every single time for each problem. Looking at the first problem, I have two terms. So I want to see, out of 14 and 42, is there a number I could divide them by? And the answer is yes, 14. That's the biggest number that divides in both. Out of the x variable, they both have one factor of x and they both have two factors of y. So one way to think about factoring is to think about dividing by this greatest common factor that we've just pulled out front. If that helps you to think about what's going to be left behind. In the first yellow term, all that's left behind is a factor of x. In the second term, when I divide 14 into 42, I'm left with 3, x's cancel, and a y. The next one, I look for a greatest common factor among my 4 terms, and I don't see anything. They don't all have some number that I can divide by or some variable in common. So instead, I'm going to group them. Usually, grouping the first 2 together and the last 2 together will work. So I look at my first parentheses. I can factor out a 6 and an m, and I'm left behind with n plus 3, because 6m times n is 6mn, 6m times 3 is 18m. In the next group, the only thing they have in common is a -1, which I'll factor out, and I'm left with n plus 3. Notice now each piece has a factor of n plus 3. So we pull that out front, and we write what's left behind in each piece. 6m minus 1. So that's my final answer when I factor that. The next one, they all have a factor of 2. So when I factor out a 2, I'm left with x squared plus 9x plus 8, which, as you know, we're looking for something that multiplies to give me 8 and combines to give me 9, which is 8 and 1. So this is my fully factored form. When you think about it, factoring just means to break something down into its smallest pieces. Like if I wanted to factor 54, I could do 6 times 9, but that wouldn't be fully factored because 6 could break down into 2 times 3, 9 could break down into 3 times 3. So fully factored, this would be 2 times 3 times 3 times 3. We're trying to break it down into the smallest pieces that we can multiply together every time we do these problems. On number 4, there's nothing in common between x to the 4th and 1, but x to the 4th is a perfect square and 1 is a perfect square. So we can apply the perfect square formula, the difference of squares, which means 1 is positive, 1 is negative. We take the square root of x to the 4th and get x squared. The square root of x to the 4th is x squared. That goes first. Then we take the square root of the second number, which is just 1. But again, we have to check each piece and say, is that factorable? Well, we can't factor a sum of squares, but we can factor a difference of squares. So this falls right down. This follows the same pattern. One's a positive, one's a negative. The square root of x squared is just x. The square root of 1 is just 1. So now I have completely broken it down as far as possible. Let's take a look at number 6. The greatest common factor is 2, which leaves behind r cubed plus 125. R cubed is a perfect cube. It's r cubed. And 125 is a perfect cube. It's 5 cubed. So the formula says, keep the sign for the first binomial, change the sign, and then our last sign is always positive. And we're going to just drop these roots right into the formula here. So r and 5. Then we're going to square r and put it here. We're going to square 5 and put it here. And then finally, we're going to multiply them together and put it here. Now I know r times 5 is positive, but according to the formula, we changed the sign here. And now we are fully factored. We cannot factor it any further. Number 7 is tricky because 100 and 9 don't have anything in common. And at first glance, you might not realize that this is 10m to the 4th squared. And 9 is 3 squared. That's a little easier to see. So using my difference of squares formula, one's a positive, one's a negative, I drop my first, the square root of the first term, 10m to the 4th. That's my first term in each binomial, and 3 is my second term. Number 8, when we try to factor it, what multiplies to give me 1 and combines to give me 1? Nothing. So this is prime. We cannot factor that. That's as far as we can go. The last thing I want to talk about is how we can apply some substitution to make factoring some of these polynomials a little bit more manageable. Notice we don't really have much trouble factoring things like this normally as long as we have decent numbers, kind of like we did right up here. This was pretty easy to factor because our middle term was linear and our first term was quadratic. If you can rewrite an expression in quadratic form, then we can just solve it like we do quadratics, and in the end go back and basically pay for that substitution. Let me show you what I mean. This problem wouldn't be so bad if it were x squared minus 40x plus 144. If that were the problem, you'd probably say, yeah, I can do that. That's no big deal. I just am finding what multiplies to 144 and combines to negative 40. But that's not what the problem is. The problem is x to the 4th minus 40x squared. So what we do is what's called a substitution. We let x equal x squared. So notice I took out x squared right here and put in x. I took out x to the 4th and put in x squared. In other words, if I were to square these, I would get right back to what I originally had. So I'm just substituting. And now I'm ready to solve this. I'm ready to say what multiplies to 144. So 1 and 144, 2 and 72, 3 and 48, 4 and 36. Remember, we're trying to get to 40. Once we see that, we're good. Also, it multiplies to be a positive but combines to negative, which means both of them are going to be negative in our list. I could keep going. 6 and 24. 7 doesn't work. 8 and 18. 9 and 16. So many factors. And finally 12 and 12. But as you can see, right back up here, we had our winning combination. So x minus 4 and x minus 36 equals 0. And then we continue to solve. If I let this piece equal 0 and add 4 to both sides, x equals 4. If I let this piece equal 0 and solve, x equals 36. So at first glance, you might think, okay, I'm done. I have my answer. But remember, we have to pay for this substitution that we made earlier. So now it's time to put it back in and say, okay, x is x squared really. So I'm going to replace them with the x squared that before I turned my x squareds into an x, now I'm going to turn them back into x squared and keep on solving. Continue with this problem. To solve this, I have to take the square root. So x equals plus or minus radical 4, which is 2. When I take the square root here, x equals plus or minus 6. So my four answers are -6, -2, 2, and 6. This one is similar because note, if I square this term, I would get this degree. Square root of x squared, pardon me, the square root of x is x. So what we're going to do, we really want our problem to look like this. So what I've done, I've said, let's let radical x equal x. And then I check it, okay, well, if radical x equals x and I square it, sure enough, I get x squared. So I've made a good substitution. And now it's time to solve. Because I have a leading coefficient that isn't 1, I have to do -30, factors of -30, like -1 and 30, -2 and 15, -3 and 10, -5 and 6, and there we have it, our winning combination that multiplies to -30 and combines to 1. So I put both of those under 2x and reduce if possible. So that my factors are 2x minus 5 and x plus 3, solving by adding 5 and dividing by 2. We can see that x equals 5/2 or x equals -3. Now we have to go back and pay for our substitution. So I'm going to take out the x's here and replace them with radical x. Now, radical x cannot equal a negative number. So we throw this away. That's extraneous. And instead, we solve this one by squaring both sides. And when we do that, x is 25/4.